Today we're going to look at how we can undo the simplex graph operation. To review, the simplex graph of an undirected graph G, denoted by K of G, is a graph whose vertices are the cliques of G, and in which two vertices are adjacent if their corresponding cliques in G differ by the presence of a single vertex. The question we'll be thinking about in this video is this. If we're given a graph H and told that it's isomorphic to the simplex graph of some other graph G, can we recover the structure of G? Before we begin to figure that out, let's make a couple observations about simplex graphs. First, in any simplex graph K of G, the vertex corresponding to the zero clique in G, which we'll denote by V sub 0, will have maximum degree, and its degree will be equal to the number of vertices in G. Note that it may not be the unique vertex of maximum degree, because there could be other vertices with the same degree, as seen in the simplex graph shown here. To prove the zero clique has maximum degree, we only need to show that no vertex in the simplex graph can have degree greater than the number of vertices in the original graph. Think back to the adjacency rule for simplex graphs. A vertex C is adjacent to a vertex W if the clique corresponding to C differs in the presence or absence of a single vertex from the clique corresponding to W. Now, if we have a clique C of size x in a graph G with n vertices, then there are at most n minus x cliques in G that differ in the presence of a single vertex from C, and there are exactly x cliques in G that differ in the absence of a single vertex from C. So the degree of C in the simplex graph will be greater than or equal to x, its size, and less than or equal to n, the number of vertices in the original graph. Now that we know that the upper bound for degrees of vertices in a simplex graph is the order of the original graph, we can say with certainty that the zero clique vertex is of maximum degree in the simplex graph. Let's keep this fact in mind while we look at the next fact, which will let us reverse the simplex graph operation. If we have a simplex graph K of G, and F is the graph we get by deleting the zero clique vertex from K of G, then G is isomorphic to the subgraph of the graph power F squared induced by the open neighborhood of the zero clique vertex, with the isomorphism defined here as the mapping alpha. Recall that raising a graph to the second power means that we make all vertices at distance less than or equal to 2 adjacent. What this means is that we can remove the zero clique vertex from the simplex graph K of G, square what remains of that simplex graph, and then look at just the subgraph formed by the vertices that were once adjacent to the zero clique vertex. At that point, we would have recovered the structure of G, the original graph. Before we prove this, let's look at an example. Here's a graph together with its simplex graph. Now if we remove the zero clique vertex, we get this graph. And if we then take the square of that graph, we get this graph. Finally, if we take the subgraph induced just by the one clique vertices, which are the neighborhood of the zero clique vertex, we get a graph with the same structure as our original. To prove this isomorphism for the general case, note that if we have a pair of adjacent vertices A and B from G, there will be some two clique that they're both a part of, which means that the two one clique vertices A and B in the simplex graph will both be adjacent to the two clique vertex AB. And the reason this is important is because it implies that if A and B are adjacent, then in the simplex graph, the one clique vertices A and B will have a path of length 2 between them that does not involve the zero clique vertex. So if we remove the zero clique vertex, A and B will still be connected by a path of length 2. If we then perform the graph square operation, A and B become adjacent. In the other direction, any neighbors of the zero clique vertex that are adjacent in K of G minus V sub 0 squared must have had a path of length 2 or 1 between them and K of G that did not involve the zero clique vertex. And since one-click vertices are never adjacent, it must have been a path of length 2. That means that they must correspond to two vertices in the original graph that are adjacent. So the images of A and B are adjacent in K of G minus V sub 0 squared if and only if A and B are adjacent in G. So alpha is an isomorphism, and our two graphs under discussion are isomorphic. We now have everything we need to undo the simplex graph operation, provided we're told which vertex is the zero-click vertex. But what if we're given an unlabeled simplex graph? We still have most of what we need. All we need is to identify which vertex is the zero-click vertex. From that point onwards, we just take certain subgraphs, use the graph square operation, and we'll recover the original graph structure. This is why the previous result on maximum degrees of vertices in simplex graphs is useful. If a simplex graph has maximum degree d, and it has a single vertex of degree d, then we know right away that vertex is the zero-click vertex, and we can find the original graph structure using the process we just described. Now what if our simplex graph has multiple vertices of maximum degree? How can we identify the zero-click vertex in that case? The trick is we don't have to identify the zero-click vertex in that case. Any vertex of maximum degree would work just as well with our process. We delete the vertex, square the resulting graph, and take a subgraph, and the result will be the same as using the zero-click vertex. Why doesn't it matter which maximum degree vertex we use? It's because if V is a vertex of maximum degree in the simplex graph, then the neighborhood of V in the graph K of G minus V squared is also isomorphic to the original graph G. To see why the structure of the neighborhood in K of G minus V squared is the same as that of the original graph, suppose we have a graph G with n vertices and a clique C of size k with n neighbors. That is, it's a vertex of maximum degree in K of G. In the simplex graph, this clique has k downward neighbors, or neighbors formed by excluding a vertex from it, and n minus k upward neighbors. That is, neighbors formed by adding a vertex to C. Let's label the vertices in C with V sub 1, V sub 2, and so on up to V sub k, and the vertices not in C with A sub 1, A sub 2, and so on up to A sub n minus k. Then the neighborhood of C looks like this in the simplex graph. Note that it must be the case that this union is the vertex set of G. Next, for distinct x and y, C plus A sub x and C plus A sub y, which are the cliques formed by adding the vertices A sub x or A sub y to C, have a common neighbor that's not C, specifically C plus A sub x plus A sub y, if and only if A sub x and A sub y are adjacent vertices in G. Similarly, C minus V sub x and C minus V sub y always have a common neighbor that's not C. Specifically, C minus V sub x minus V sub y. And it's always the case that V sub x is adjacent to V sub y in the original graph. This is because they're members of the same clique. Finally, C plus A sub x and C minus V sub y always have a common neighbor that's not C. Specifically, C plus A sub x minus V sub y. And it's always the case that A sub x is adjacent to V sub y in the original graph. What we have now is that the neighbors C plus or minus V and C plus or minus W have a common neighbor that's not C if and only if V and W are adjacent in G. And remember, having a common neighbor that's not C is equivalent to being adjacent in K of G minus C squared. So the mapping alpha shown here is an isomorphism. Together, this means that we don't need to find the zero-click vertex in order to recover the original graph. Any vertex of maximum degree works. Let's do an example. This simplex graph has multiple vertices of maximum degree. What's its original graph? First, choose any of the maximum degree vertices. Let's use C. Remove C from the graph, and then take the square of the graph. Then find the subgraph induced by the vertices that were adjacent to C. The result is the original graph, which we can verify for ourselves by finding its simplex graph. I encourage you to perform the same operation using the other maximum degree vertex, F, and see that the original graph obtained is isomorphic to this one. Now that we have our method to find the original graph structure given a simplex graph, what are some possible uses of this method? For one, it gives us a roundabout way to check whether a graph is a simplex graph. First, assume the graph's a simplex graph, and then apply our method to find the original graph. Then, take its simplex graph and compare with what we started with. If the results don't match, then we did not have a simplex graph. Also, our method implies that two simplex graphs are isomorphic if and only if their original graphs are isomorphic. In a future video, we'll see how this method can be useful to find out whether simplex graphs can be products of other graphs. That's it for this video. Thanks for watching. If you enjoyed this video, please subscribe and click the like button. Have a great day.